Welcome to our comprehensive breakdown of the major threats facing artificial intelligence systems. In this session, we will explore the vulnerabilities that exist when we build an artificial intelligence, when we run it, and when end users interact with it. Understanding these threat profiles has immense practical value for your career. By mastering these concepts, you will be equipped to advise your organization on whether a new automated tool is actually safe to deploy for office workflows, and you will know exactly what security questions to ask external vendors before signing a contract. The industry standard framework divides artificial intelligence vulnerabilities into three primary attack surfaces. An attack surface is any digital location where an unauthorized person might try to break in or cause damage. The three surfaces are development time threats, runtime security threats, and threats through use. Development time threats occur while the system is actively being built. This is the construction phase. Vulnerabilities here involve the engineer workspaces and the supply chain where raw information is gathered. Runtime security threats target the conventional computer systems that host the model. Artificial intelligence requires standard web servers, software wrappers, and network infrastructure to operate. If a hacker exploits a traditional software flaw to access the server, the artificial intelligence is compromised, regardless of how well it was designed. Threats through use happen during routine daily operations. This focuses on the information people type into the system and the answers the system provides back to them. Let us examine the first major development threat, known as training data leakage. Training an artificial intelligence requires massive data sets. Data leakage happens when this highly sensitive information is stolen or copied out of the secure workspace. This usually occurs because of weak access controls somewhere along the digital supply chain. The leak might happen at the original collection source, during the data cleaning process, or directly from the programmer workstations. To understand this, imagine a high-security kitchen where chefs are testing a secret recipe. If the kitchen doors are left unlocked and an assistant walks out with a bag of secret ingredients, that is data leakage. In the tech world, data scientists use highly flexible testing environments. Because these platforms prioritize convenience, a simple command can accidentally or intentionally transfer thousands of private records to an external cloud drive. This unauthorized outward transfer is a highly technical term called data exfiltration. Organizations must build strict network barriers to prevent exfiltration from happening. Next, we have poisoning attacks. These are divided into data poisoning and model poisoning. Data poisoning means deliberately injecting malicious or corrupted information into the training dataset to manipulate how the final system behaves. Finding these bad records is incredibly difficult because datasets are enormous. Attackers can introduce this poison at the data source through a compromised data broker by intercepting network traffic or during the data cleaning phase. There is also a huge risk when using in-context training, which is a technique where the artificial intelligence reads external documents to find answers. In the industry, this is often called retrieval augmented generation. To understand this vulnerability, imagine giving a student an open book test. If an attacker sneaks false information into that specific textbook, the student will confidently give the wrong answer. The ultimate impact of data poisoning is either a secret backdoor that triggers bad behavior on command, or general sabotage that ruins the reliability of the entire system. Model poisoning is a completely different approach. Instead of corrupting the raw information, the attacker directly tampers with the mathematical parameters, the core architecture, or the software libraries of the model itself. This can also happen if you purchase a pre-trained system from a vendor that was tampered with before delivery. Preventing direct model poisoning requires exceptionally strict access controls to the core programming environments. Our next vulnerability is model theft. Creating an artificial intelligence is a massive financial investment. Stolen models are highly valuable intellectual property, and they help hackers plan future adversarial attacks. An artificial intelligence is essentially a highly complex mathematical formula represented by software code and configuration files. The most obvious form of theft is a hacker breaking into a server and illegally downloading those exact files. However, an attacker can also steal a model without ever breaking into the server. By sending thousands of carefully designed questions to the system and analyzing the exact answers it gives, the attacker can reverse engineer the mathematical logic. They use this analysis to build an exact digital clone. It is exactly like a rival chef visiting your restaurant every day, tasting your signature dish, and eventually figuring out your exact secret recipe without ever stepping foot inside your kitchen. We will now cover threats through use. The most common is the prompt injection. This attack targets generative systems by using specifically crafted text commands that manipulate the system into ignoring its original safety rules. It is similar to hypnotizing a loyal guard into opening a vault by convincing them you are their new boss. These attacks are incredibly popular because anyone can attempt them through the normal user interface. An indirect prompt injection happens when the system reads a seemingly normal file that contains hidden, malicious instructions. To defend against this, developers build structural templates that sanitize user inputs, and they install filters that monitor and block inappropriate outputs. Next is model evasion. This happens when an attacker intentionally alters their input to slip past the detection capabilities of the artificial intelligence. For instance, if an automated filter blocks certain keywords, an attacker might slightly misspell those words to bypass the filter while still conveying the malicious message. The goal is to force a misclassification. While evasion tries to trick the system, model inversion tries to extract highly confidential information from it. The attacker feeds in slightly modified inputs, observes the responses, and works backwards to deduce the hidden inner workings. Through this interrogation process, the attacker can achieve attribute inference, which means figuring out sensitive details about the people in the training data. They can also achieve membership inference, which is mathematically confirming if a specific person's record was used. In extreme cases, they can reconstruct near-perfect copies of the private training data. Many companies do not build their own systems from scratch. They purchase vendor-supplied artificial intelligence out of the box. When you buy a pre-built system, the vendor handles the security of the training phase. However, if that vendor suffered a data poisoning attack before you bought the software, your organization will still suffer the negative impacts of that compromised system. Finally, we must consider artificial intelligence solution disruption. Attackers can cause massive operational damage by flooding the system with a massive volume of requests or sending incredibly complex math problems. This consumes all the computing power and creates a denial of service. The system becomes so overwhelmed that it crashes and denies access to legitimate users entirely. Let us summarize what we have learned today. We explored how the development phase is vulnerable to data leakage and covert poisoning. We discussed how entire systems can be stolen through direct hacking or complex reverse engineering. We examined operational threats like prompt injections that break the rules, evasion tactics that hide from sensors, and inversion attacks that steal privacy. Finally, we highlighted the shared risks of using third-party vendors and the danger of overwhelming the system to cause an outage. All the vital topics and technical concepts from this session are extensively tested on the ISACA exam. To ensure you are fully prepared, I strongly encourage you to log on to rucloud.com, solve the chapter-specific multiple-choice questions to reinforce your knowledge before advancing to the next video module. Thank you, and I will see you in the next session.